Okay, well today's the 26th of October and we're going to talk about limits of these functions of two variables, okay? Blush? Somebody's allergic to limits of functions of two variables. Violently so. All right. Math team today, okay, as well? Pizza? Okay, back in Calc 1, when you did a limit, as x approached c, you approach c from the left and from the right. And if what happened, the function approached the same value, and in this case it would be simply f of c, whether we approach c from the left or right, that value was the limit. The limit of this function here, as x approaches c, is f of c. There's nothing strange happening there, okay? It's not a point of discontinuity. As long as the function's continuous there, that is the limit. You just substitute in. You'll have homework on WebAssign. That's going to be the same thing. They'll give you this kind of homework. They'll say the limit as xy approaches 3, 2 of, let's say, x squared plus y squared. Well, there's nothing weird happening there. Okay? You let x go to 3, the x squared will go to 9. You let y go to 2, the y squared is going to go to 4. That answer is 13. Okay? Not a problem. All right? Not a problem. However, in 3 space, and as well as what you did in Calc 1, what happened? When was there a problem here? There was a problem back in Calc 1 when you had this kind of a limit. Okay? As x approaches 3. What's the graph of this thing look like, by the way? What's the graph of that? What is it? There's not really an asymptote at 3. Yeah, it's a removable discontinuity at 3 because what happens is...
That's just a linear line.
Yes, it is a linear line as opposed to those wiggly lines.
Yeah.
All right. As x... What you did here, you said, oh, the numerator is going to 0, the denominator is going to 0. We have to do something here, okay? We have a 0 over 0 indeterminate form. And that word indeterminate is really important here. Indeterminate means what? It's not uniquely determined. It could be anything, that indeterminate form. Okay? That 0 over 0. So what you did is factored it. You canceled out these x minus 3's. And when you crossed them out, what does that do to the graph? That removes that point from the graph. It's exactly what Eric said. It's a removable point of discontinuity. The graph looks like this. That point has been removed. That point is 3, 6. Okay, bless you. Now, what's the limit as x approaches 3? It doesn't matter we approach 3 from the left or the right. The limit's going to be equal to 6. Okay? As long as the limit existed, that's a removable point of discontinuity. What does that mean? That means you can take out the discontinuity, remove the discontinuity, by defining the function to be equal to the limit at that point. If you define the function to be 6 at 3, function's continuous there. Okay? It's continuous. All right, that's back in Calc 1. What happens in Calc 3 now when you have these this problem? Well, let's take a look. Let's suppose we have, well, let's say x squared plus y squared over x cubed plus y cubed kind of thing. Now, where's the numerator going as xy goes to 0, 0? 0. And where's the denominator going? 0 as well. We got a 0 over 0 indeterminate form. But you know what? We don't have a factoring possibility. We can factor the sum of 2 cubes, actually. X plus y times x squared minus xy plus y squared. But it doesn't cancel anything here. So what are we going to have to do here?
Did you do something with like a conjugate?
Oh, conjugate's a possibility too. That is a possibility. It just leads nowhere here. It's a good suggestion though. It's a really good suggestion. Here's what we're going to do though. If we can't do a factoring and we can't change it in some way, we're going to have to take a look at approaching that 0, 0. Now, in a function in a single variable, you only have two directions to approach the c, left and right. How many different approaches do we have to the origin if we're in the xy plane? More than 4. How many different approaches do we have? We have an infinite number of approaches, yeah. We've got 4 along the axes, that is true. That's true. But you know what? You've got an infinite number of linear approaches to the origin. Okay? All these lines in this xy plane approaching the origin. But not only that, you have more than linear approaches to the origin. You have parabolic approaches. You have trigonometric function approaches. You have exponential function approaches. You have an infinite number of choices. All right? I mean, a lot of ways. So,
That's when we throw
what are we going to have to? I know.
Close the book. We're done.
That's it.
Time to quit, guys.
So here's what we're going to do. We are going to look at linear approaches to the origin. Okay? We're going to take linear approaches to the origin. And one of two things will happen when we take these linear approaches. One thing that could happen is we get 2 different limits depending on which line we use to get to the origin. If that happens, the limit does not exist because different lines approaching the origin gave us different limits. And when that happens, forget it. There is no limit. The other possibility is it doesn't matter which linear approach we take. We get the same limit all the time. In that case, here's what we're going to say. Under linear approaches to the origin, we get such and such as a limit. It doesn't guarantee that that is the limit. It could be that a sine wave approach gives us something different, believe it or not. So here's what we're going to have. We're going to have 2 possibilities here. If we can't factor it and we can't cancel out the common factor, we're going to take linear approaches and we're going to see what happens when we approach the origin along these lines. So let's take a look at that. Here we go. And how do we do that? We do that by doing the following. We're going to let y equals mx. This is the whole family of lines in the plane that goes through the origin. Let y equals mx, where m is the slope of a line. So we'll take the limit. It's xy approaches 0, 0. X squared. Okay. We'll have x squared plus y squared. Oh, let. That's a let.
I couldn't tell if it was an H or like a
Hit y. No, it's a let. It's a capital
I
L.
thought it was like net for a second. It was a really weird. Like,
Yeah.
I don't know I. But
Yeah, the E is not well formed either. It looks, it's pretty sloppy. You're right. You're right, Teddy.
No, it's not bad. I mean,
That's bad. You're being kind.
Should have known it was a vector, but.
Y cubed, m cubed, x cubed. Okay.
I probably just started laughing.
And let's see, what can we do here? We can factor out an x squared on that numerator. So we can factor out an x squared. You get 1 plus m squared. Factor out an x cubed in the denominator. Okay. We can cancel out some x's and be left with, we're going to have to go to the next page. You guys all set here?
Wait 1 second.
All right, so what we can do is go to the next page.
Does it matter if you choose to set
y or x equal?
Doesn't matter. Almost always, though, what we're going to do is let y equals mx, just the usual way to do it. Does not matter, though. This is the limit as xy approaches 0, 0. We can cancel out some of those x's, and we're going to be left with this. Okay? Now, as xy approaches 0, 0, m is a constant. It's the slope of these lines. Where does this go as xy approaches 0, 0? Infinity. Because the denominator is going to be going to 0. X is going to go to 0. The m's, okay, whatever constant they are, it doesn't matter, as long as the x is going to go to 0. This is going to go to infinity. Not only does it go to infinity, it goes to positive infinity if we approach 0 from the right. It goes to negative infinity going from the left. Okay, it goes to two different infinities. The answer here is this limit does not exist. Okay, that limit does not exist. Okay, how's that look?
So you can't do like a L'Hopital's rule with the multivariable.
Say that again.
You can't do like a L'Hopital's rule with the
There is a version of L'Hopital's. We don't get into it at all, though. There is a partial derivative version of L'Hopital's which we don't use. Although I got to tell you, it's possible that you end up with a function of x's here and a function of x's here, and you can use L'Hopital's on that, because as long as it's a single variable, that's a good call.
So the strategy here is to kind of like just make y equal mx and then take that out and then kind of you're just solving for x at that point.
Yeah, exactly. That's exactly the strategy. Let's do another one. That's exactly what we're doing now. Let's do something like this. How about the limit? xy goes to 0, 0. How about 3xy over x squared plus y squared? Now here's another one. The numerator is going to be going to 0. The denominator is going to 0. We end up with a 0 over 0 indeterminate form. First thing to do is see if you can simplify by factoring or doing something. There is no simplification here. So what are we going to do? We're going to take linear paths to the origin. And we're going to let y equal, let's see, let y equal mx to get the limit. xy goes to 0, 0. 3x mx over x squared plus, bless you, y squared. That's equal to the limit. xy goes to 0, 0. Let's see, what do we have? We have a 3mx squared, and here we can factor out an x squared and get 1 plus m squared. Now what can we do? You bet we can. Cancel out those x squares. And we get the limit as xy goes to 0, 0 of 3m over 1 plus m squared. Well, what's this limit of 3m over 1 plus m squared as xy goes to 0, 0? 3m over 1 plus, yes, m squared. Tell him with it. He was there. He was getting there. He was getting there. He was just taking his time. All right, that's all. Why? Because there's no x's in there. There's no x's, just a bunch of constants. Whoa, Nick.
Question. So as x goes to 0,
Yeah.
why do you write it again in 0? Comma 0?
Right here.
Yeah. Why do you need a y?
You know what? I don't really, once I eliminated the y's here. It's just that we're approaching 0, 0, these ordered pairs. You know what? It would not be wrong to put x approaches 0 once I eliminate the y. That's a good point.
So x just disappears? This one, where does it go?
The x disappeared back here,
Yes.
okay, because we canceled
Oh,
them
you
out.
canceled out, that's right.
Yep. And now we have no more x's, okay? And if we have no more x's, as xy goes to 0, 0, m doesn't care, okay, because there's no x's in this expression. So what happens to this? It's equal to 3m over 1 plus m squared. Now, what does that mean as far as the limit is concerned? It depends on m. Let's suppose m is 1. If m is 1, we get 3 halves. That will be the limit. So if we approach the origin along the line y equals x, that surface, that thing is going to approach 3 halves, okay? That limit will be 3 halves. If we approach the origin along another line, y equals 2x, say, now y equals 2x would be the line over here. If m is equal to 2, we're going to get 6 over 5. We'll get 6/5. So now if we approach the origin along this line here, it's going to go to 6/5. Depending on which line we approach the origin on, we're going to get different limits every time. Okay? It's kind of, I think Wednesday what I'll do is bring the computer in so you can see a graph of something like this, and you can see what happens around the origin. You get these wrinkles, you get these cusp points, you get these things that it's really kind of weird because it depends on how you approach the origin, you're going to get different limits, right? Wait, so we need, where's Dan?
We talked about.
He was sitting there, but then you started teaching and he just got up and left.
There should be no mathematics today, so
Oh, man.
Insulted.
He was insulted. Dave,
Actually, I had 2 questions.
2 questions.
Was, is m sort of a common constant to use? So if we have an answer in WebAssign, will they ask us to use a variable if we just enter m in?
Okay, well, here's it. What is the answer to this question?
It doesn't exist.
Does not exist.
Okay.
So that,
Possibilities.
no, if m will never be a possibility here because that would mean the limit changes depending on m, okay?
Right.
So you'll never have m as a possibility, so it won't matter what you use, k or m would be the 2 usual choices. It won't matter. Either you end up with a limit, and which I haven't done yet, and we will in a second. We'll do one where we get a limit, or else the limit won't exist. But in neither case will it depend on m. Will m be part of your answer?
Then my other question was, when you decide what to set y equal to, do you base that off of what's in the numerator?
No. It is always the case we're going to use linear functions of the form y equals mx.
Because the denominator is quadratic.
Doesn't matter. Always we're going to do that. Y equals mx. We're going to take linear paths to the origin.
With the last one, didn't we do y equals 1 plus m squared?
No, we did y equals mx.
No.
Yeah, we'll always use that. The actual limit, if you were to prove, see, what we're doing here is saying, okay, along linear paths, either we don't get a limit because 2 different linear paths lead us to 2 different limits, in which case there is no limit, or along the linear paths we have a limit. If you really want to, do we have any math majors here? Yeah, you know, there is a definition, a delta epsilon definition of limits here, where you would prove that along any path you get the same limit. Much more complicated than it is in Calc 1. Something we should look
Let's
at.
use a different substitution for y equals mx.
No, you wouldn't even use a substitution at all. You would use a definition of the limit and try to prove the existence of some epsilon greater than 0 such that the difference between the function f of xy and the limit is less than epsilon whenever the xy's get to within a delta of the origin. It's a yeah, delta.
So it gets really crazy if you don't use linear lines,
Yeah.
basically.
Yeah, you got to prove it for everything. See, we're just doing it for lines. We're just looking at linear functions. And I got to tell you, what I'm doing here is like, here's the engineering calculus usually doesn't even do this at all, okay? And the math calculus proves it for everything. So we're doing something like in between the two is what we're doing. Yeah. maybe.
So for any 2 points, in regards to the origin, you solve for m, and you get that slope, and depending on that slope, you plug in that formula, and that's what your limit's gonna be at the origin?
You don't even need to take 2 points to find the slope. All we're doing is saying let y equals mx, any slope at all. Let's see what happens as we take these linear approaches to the origin. If we get 2 different limits, we know the limit doesn't exist and we're done. But if we get the same limit, we can't say that is the limit under all paths. All we can say is that is the limit under linear paths.
Yeah, but for this instance specifically, if you were to find the specific limit, you'd have to solve for m, and then plug it into that, what we got.
No, what do you mean now?
I know you're saying we're not gonna have to end up doing this, but if you have 3m over 1 plus m squared is your limit for any solution of m, to get that m, you have to have a y and an x coordinate and then solve for m.
Yeah, okay, I see what you're saying. No, but we're never going to do that. Here's what we're doing. We're saying, okay, this limit depends on m. Different m's, different limits. Therefore, the limit does not exist.
Okay.
That's all we're doing.
Okay.
Yes?
So for the case where we can say that it does approach a limit, would have to be just like a constant?
Yeah, you want to, let me do one. So far, we've got 2 DNEs.
Yeah.
Let's do one where there is going to be a limit under linear paths. Go ahead.
Question. We're solving for the limit by looking for it on a linear path. Like, could we find it on a polynomial path?
There are polynomial paths. Y equals mx squared. You could take second degree, third degree. It is conceivable that you have a function where you, under every linear path, you get the same limit, but under a second degree, a quadratic path, you get something different, and therefore prove the limit does not exist. That is possible. We're not going to go there. All we're doing is saying, under linear paths, does the limit exist or not?
So it's kind of just like a false.
Yeah,
like you don't know for sure. You're just kind of like, oh.
Yeah, so
Yeah,
we're
there's
like
no,
half proving the limit at this point?
Well, here, what? What we're
fooling
saying
yourself.
is, actually, if the limit is different, we can say definitively there is no limit. We are accomplishing
Yeah,
that.
that's true.
On the other hand, you're right, though. We're taking linear paths only.
Yeah, we're restricting it.
Yeah, we're just doing that. We're just taking linear paths. And that's it. That's all we can do. That's all we're going to do. That's all we can do.
So what will be the point of this if we're learning this for linear paths, but if like later on a mechanical engineer wants to use this, you just
Here's all we need. Here's what we're doing. We're doing this only because when we do the partial derivative, it's a limit definition. So we'll need the limit there in order to define our partial derivative. It's just like we did in Calc 1. What do you do in Calc 1? You do some limits. And what do you do in Calc 1 for limits? You ever prove them with a delta epsilon proof, which is the actual proof? No. What you do is you do it by doing the factoring, eliminating the 0 over 0 indeterminate forms, and doing that. Do you actually do a proof, though? No. That's another thing we should do. We definitely do this. We don't. But what we do is good enough to define the derivative and use that definition of a derivative to give us the properties of the derivative that we need. And that's exactly what we're going to do here. What we need it for is to do the partial derivative, which is a limit definition, right? And we need that definition of a partial derivative, and then we're going to have some rules for partial derivatives, so we don't need the definition anymore. So it's the same. We're following the same path that you do in Calc 1. That's what we're doing. Now, as far as problems are concerned, are there any problems? No. There's no problems dealing with limits that we'll ever do. That you will ever do. You will never do them. A math major possibly would do them in a real analysis class after this.
By problems, do you mean like word problems?
Well, they're not. Yeah, they're kind of word problems. Yes, they are. They're kind of word
We
problems.
would be asked to solve one like this on the exam.
On the exam, yes, I will give you something like this. And the answer is does not exist on this one. Let me give you one where the limit does exist. Well, you guys, this is the first class I can remember that actually pushed back on this and said, listen, Burns,
I thought I knew so much about calculus. I realized I don't.
Yeah, that's pretty good. Engineering, I got to tell you, engineering calculus, the applications are paramount. They're what's important. The theory behind it, the proofs, in some engineering calculus, they don't do any proofs at all, nothing. And, it's all applications. I think you guys, I do some proofs, we do some definitions. This is a midway between the two limit things, you know what I mean? So
you're shortchanging me, Burns.
yeah, the math majors, yeah, you're right, this is engineering calculus, not math major calculus. And there's some differences, yeah.
Oh,
Where
I
are
gotta
you
look
going
fucking
next year?
smart.
Where are you going
I'm
from
going to
here?
Westfield State.
Westfield State? All right, then we've done way more than they do, so there you go. No. Oh, all right. No, there's a couple of things we should look at, seriously. We're going to have to do this.
Maybe we can just like keep continuing math club and we can do some math stuff.
Well, that's possible. I'm thinking about January. Where are you going in January? What are you doing in January?
Sitting at my house.
Keeping warm, right?
Hell yeah, dude. I'm not going anywhere.
I'll tell you what. I'm going to be here.
Calculus.
What?
I said remedial calculus.
We should be taking a look at that definition of a limit with delta epsilon
Can
proofs.
we all come?
Yeah.
Sure, you're all welcome.
Can we do it right after?
If you want to be a math major after my
You should make an intersection course.
because you
with just
inspire me,
proofs.
Burns.
Wow, that'd be stunning. That'd be cool. Well, I am going to be here for those 6 days in January. And even if you don't sign up for the Mathematica programming thing, I think we should take a look at you coming up here, and we're looking at some of these delta epsilon things.
All right.
All right. Okay. All right. Let's do another one. Let's do one where we actually have a limit. Somewhere we haven't had a limit. Let's take a look at this one. Let's take a look at xy squared over x squared plus y squared.
Will it always be 0, 0?
Yeah, 0, 0 is the only thing that's interesting. As far as these are concerned, you may have something like I did in that first example. We're approaching 3, 2, and you just substitute in. I mean, that's not fun. That's not interesting. You just chuck them in there. The only ones that are interesting are the 0, 0s, okay? The 3, 2s and anything else is just hardly worthy of your time. You know what I mean? Okay, let's take a look at this one. The thing to do is look at the numerator and denominator. Where's the numerator going? 0. And where's the denominator going?
0.
Thank you. We got 0 over 0. So let's take our linear paths. Let's let y equals mx. Okay, let's see what we get. X, m squared, x squared. It's our y squared. X squared plus y squared, m squared, x squared. That's the limit. xy approaches 0, 0. Let's see. We've got an x squared here and an x here. Let me write it this way. So I've got x cubed, m squared. And I've got an x squared and a 1 plus m squared. Okay? How's that look? Okay? So what can we do now? Cancel out some x squares. We'll cancel out some x squares. You get x m squared over 1 plus m squared. Now, let's see what's happening here. You've got m squared over 1 plus m squared. M is some constant. Different m's will give us different numbers for that m squared over 1 plus m squared. But they're all getting multiplied by x. And what is x doing? Where is it going? 0. Doesn't matter what m is. As long as x is going to go to 0 here, what is that limit? 0. That limit does exist and is equal to 0 under linear paths. Okay? And that's all we can do is say under linear paths, that limit is 0. It's conceivable under a sine wave that it's something different. Okay? And that's what we're going to do. Under linear paths, that answer is 0. I believe that's all WebAssign is asking you for too, is linear paths. Okay? Yes?
Are we gonna be doing any other ones?
Other than linear paths?
Yeah.
No.
This whole chapter.
No, this chapter is about finding partial derivatives and gradients and directional derivatives. But we need this limit to do our partial derivatives. See, here's the thing. Here's the problem. In Calc 1, you have y as a function of x. What is the derivative? It's the slope of the tangent line to that graph. It was how fast y was changing with respect to x. Y only had one direction to go in, and along the x-axis. But what do we have here in Calc 3? We have a function of xy. We have a surface. Okay? Take a point on this surface. We've got a whole bunch of tangent lines on that surface. Say you got a surface going like this. Or take that paraboloid we had from the other day. Starting at the origin, coming out this way. Okay? With bold from here. Take a point on that paraboloid right here. What do we have for slopes of tangent lines? Well, you've got this slope of a tangent line. But you also have this slope of a tangent line. You have this slope. All these lines intersect the surface at exactly one point. Okay? We got all these slopes of tangent lines. Yes, we do. If you take, that was nice. If you take all these tangent lines to the surface at that point, you get a tangent plane. That's what we're going to end up with. We're going to end up finding the equation of that tangent plane to that surface at a point. Okay? We got an infinite number of tangent lines. So the question is going to be, which one do we care about? Well, we may care about a tangent line in the x direction along the x-axis. That's the partial derivative of that function with respect to x. What does it mean? It means let's find the slope of the tangent line in the x direction and hold everything else constant. Hold the y constant. It's that slope of the tangent line. And along that paraboloid, it may be something like this. Okay? Depending on where I have it exactly. It may be something like it's 0, the slope of the tangent line in the x direction. What's the slope of the tangent line in the y direction? Okay, that may be that would be something else. Or maybe we want the slope of the tangent line in this direction, okay? In Emmanuel's direction. That's in the book. I think it's the partial derivative with respect to Emmanuel. All right? So that goes in this direction. We're going to also be interested, where's the maximum slope of the tangent line? Okay? Well, on that paraboloid, you can imagine, if you can picture this, it's going to be in Emmanuel's direction. That's the maximum slope of the tangent line. We're going to have 0 here, 0 here, and we'll have other things, but it's only in that direction we have a maximum slope of the tangent line. Where is that going to be used? It's interesting where that's used. That direction of the maximum slope of the tangent line is called a gradient, and that's one thing we're going to be doing in this chapter. If you're working for Raytheon, right, big defense contractor outside of Boston, and you're designing heat-seeking missiles, okay, Patriot missiles, I'll tell you, what do you want that missile to fly in? You want a missile to fly in the direction of maximum temperature difference, right? Because you're seeking to find a missile or something that has a high temperature, that engine, okay? So what do you do with your Patriot missile? You fly in the direction of the gradient, okay, the very thing we're going to find. I had a kid come from here, right? I had a student from here a long time ago. I don't know what it was. Really great student, right? Really great student. Not as good as you guys, but really, really good student. And he went to Raytheon. This was around 1990 or so, when we were doing the Gulf War thing, right? Patriot missiles. And he came back to visit me, and I said, well, how's it going? He said, all right, great job. He's an engineer with Raytheon, working on some cool stuff. I said, well, what are you working on? And he said, I can't tell you. Yeah, I know, that's exactly what he said. I can't tell you. I said, oh, okay. Hey, don't tell me. But I suspect it was something to do along those lines, you know, with heat seeking and along a gradient. But he did say, he said, this I can tell you, I did use some of that Count 3 stuff. So, there you go.
What happens if you disappear?
What's that?
This was recorded.
We'll know what happened.
Oh,
That's it. See you guys. Oh, well. All right. So, anyhow, do this, and tomorrow I'll answer any questions you have. And Wednesday we're going to start doing partial derivative, which will lead eventually to the gradient.
Wow.
See ya.
Sophia will be so impressed.
I'm just kidding.
So what was y'all?